The VSL retained earth system, or VSoL for short, is a proprietary reinforced soil system utilising either concrete panels or steel mesh facings tied into a tensile reinforcement to produce a cost-effective alternative to conventional concrete structures, such as piled retaining walls, cantilever retaining walls, and mass concrete retaining walls. Since the system was developed in California in 1981, over 4 million square metres of VSoL have now been constructed worldwide in a wide variety of applications. Typical applications would include highway and rail structures, both in embankment and cutting. Bridge abutments may also be constructed, either carrying the load from the deck directly onto the reinforced earth, or as hybrid structures with piles encased in the reinforced mass. Heavy industrial uses in material storage facilities and mining applications are common, often incorporating high loadings from the vehicles used, while grade separation and landscaping retaining walls are also common structures. The panels used in the walls are typically squares, rectangles or hexagons, with an area of 2 to 2.5 square metres. A wide variety of finishes are made possible by using raised relief and ribbed moulds to give sharp architectural features, while rubber formliners may be used to produce more complex finishes. Acid etching or exposed aggregate finishes can provide complex texturing, whilst colours can be applied either as a pigment in the concrete or through the application of a paint to the finished panels. The reinforcement used in the VSoL system consists of either an inextensible galvanized steel mesh or a relatively inextensible polymeric strap system. The construction of the VSoL system is relatively straightforward, using minimal labour and plant. Construction commences with the formation of the levelling pad. Rudimentary timber shutters are formed, creating a 300mm wide by 150mm deep unreinforced concrete levelling pad. The upper surface of the pad is smoothed by hand. The purpose of the pad is non-structural. It is there purely to ensure a smooth level base and guarantee the alignment of the first row of panels. Once the concrete is cured, the formwork is struck and the base is ready to receive the first row of panels. With rectangular panels, construction would continue in a linear fashion, from one end of the wall to the other. However, with hexagonal panels, first the half panels are placed, then the full panels are slotted in between them onto the alignment pins. A simple timber clamp is used to fix the adjacent panels together, whilst wooden props and wedges are used on the first row only to prevent the panels from rotating forward during initial compaction. Prior to backfilling, a geotextile is installed along all the joints of the panels. First an adhesive is placed, and then a 150mm wide strip of non-woven polymeric geotextile with a very fine pore size is adhered to all the vertical and horizontal joints, and any angled joints in the case of hexagonal panels. Alternatively, a closed cell foam strip is inserted into the panel joints to prevent loss of fines whilst maintaining face drainage capability. This procedure would be carried out at every level of the wall prior to filling, to prevent the loss of fines through the 20mm joints between the panels, and any staining of the face that this may cause. Backfilling and compaction will continue up to the level of the clevis on the rear of the panels. The correct mesh designation for the particular location on the wall will then be carried onto the structure, and the mesh positioned with the end loops slotting between the clevis projecting from each panel. Ensuring that the end loops and the clevis are perfectly aligned, a pin is driven through to provide a positive connection. Any slack is then manually removed from the mesh, whilst timber or plastic wedges are driven into place between the end loops and the panel to ensure that further slack may not develop, thus ensuring the panels do not rotate during construction. In the polymer strap system, a single continuous loop of polymer strip is run from the rear of the structure to the face and tied into the panels using a connector loop and toggle system, similar in arrangement to the clevis connector. Ensuring that the plant does not traffic directly on the reinforcement, the backfill will be placed and then spread by excavator. Immediately behind the panels, a lightweight plate compactor will be used to compact the fill material, ensuring that panels are not rotated. Within the first 1.5 meters from the panels, a lightweight vibratory roller will then be used, whilst the remainder of the structure will be compacted using a larger, smooth drum vibratory roller. Here the heavier compaction will not have a great influence on the face of the wall. Construction proceeds quickly and easily, with rates in the order of 25 to 30 square meters per day easily achievable by a gang of 4 labourers with associated plant. Here we see the special top panels being fitted to tie in with the road alignment. The VSoL system was initially designed for use in the American market. Its success there led to its use in Europe and Australia, where further success has now prompted a greater emphasis on the promotion of the system in other parts of the VSL network. More VSL profit centres are now focusing on VSoL applications, and the benefits of VSoL solutions are being applied to an increasing number of projects around the globe. VSoL market development has been particularly successful in the Asia-Pacific region and Chile, while the United Arab Emirates have experienced great success with the VSoL polymeric system in particular. In Asia, VSL Hong Kong have worked on 17 different contracts in the last 5 years. VSL India have introduced the VSoL solution to the market and are currently working on projects with a combined face area of over 125,000 square meters. With numerous projects completed in Thailand, Indonesia and Vietnam, and the first VSoL projects completed in Malaysia, the Philippines and Singapore, VSL is now firmly established as a wall supplier and installer in Asia. In Australia, VSL have been particularly successful with VSoL in Queensland and New South Wales, where the recent M7 Westlink project in Sydney used 21,000 square metres of VSoL on 45 structures.